You're almost there. You're almost full screen.
There we go.
There you go.
No, I had to acknowledge your recording. All right, so thanks, Robert, for inviting me. It's like I said, it's a pleasure to be here. This talk is about space resources. But before I get into space resources, having spent 30 years in the space transportation business, by that I mean building and launching rockets, I have to start with a rocket video. And so I'm going to stop sharing, and Robert, if you can play the video link I sent you.
Sure enough, here we go.
We are so excited to have been selected to fly this Lucy mission. It is humbling to be entrusted with something like this that is going to shed new light on the origins of our solar system by visiting primordial material gathered by the Lagrange points of Jupiter as it formed the early solar system. This is so exciting for us. Our team has worked so hard. We are honored to work with the brilliant people at NASA who put this together.
We're starting a 12-year journey of this amazing spacecraft, really 8 missions in one. For me, as we are launching this, I think of the amazing team that brought it together. On the rocket it says Lucy Strong, and for me that's the battle cry that brought the team together. Congratulations to everybody.
Go Atlas.
Go Centaur.
Go Lucy.
3, 2, 1, 0. Liftoff. Atlas V takes flight, sending Lucy to uncover the fossils of our solar system.
Tower clear. The vehicle has begun the pitch yaw. We have indication of successful separation of the Lucy spacecraft.
All righty. So what do you think of that? Are you awake now? So with that video of a cool rocket launch that happened just about a month ago of the Lucy spacecraft that's going to go tour the asteroids out in the what we call the Greeks in the Hilda belts around Jupiter or near Jupiter. I can make my first point. Space is cool. It's fun. And it's a great way to spend your career. And I've been blessed to have been in the space business for about 35 years now. And if you're a space geek like me, then that's all you need to spend 35 years in the business. But there are actually logical, rational reasons for humans to pursue development of space. And one of those reasons is space resources. So what are space resources? At the Colorado School of Mines, we take a pretty broad view of it. You know, one of the obvious resources in space is location. It's kind of like real estate, location, location, location. But a satellite in, say, geosynchronous orbit about the Earth can act as a relay. It can see from that location, you can see about half the Earth, and it can transmit signals from a TV broadcaster to a satellite dish on your home, for example. So that's one obvious resource. If you're in a space station like the International Space Station shown there, then other resources include microgravity. You can do things outside of the gravity of Earth. You have a hard vacuum. and you also have a location. In low Earth orbit, you actually have a closer view of Earth than you do at geosynchronous orbit. An obvious resource that comes from space are photons. Sunlight is a resource that we can turn into electricity here on Earth or in space. Our closest neighbor is the moon. The moon is rich in resources, and I'll talk a lot more about the moon in a few minutes. But there are minerals, there's regolith, which basically is crushed rock or lunar soil, and they're volatiles. Those are materials that, like water or other things that you can turn into gases. The poles of the moon also contain water and other volatiles like methane, carbon dioxide, ammonia. There's a bunch of stuff that's been trapped at the poles of the moon. And then if we go a little further out into near-Earth asteroids or the asteroid belt, many asteroids are made up of hydrated minerals that contain water, which we call hydrated minerals. And you can break the chemical bonds and get the water out. There are also metallic asteroids, other minerals. Some asteroids may even be remnant comets, which means they would be composed of ice or ices. And then if we go further out to Mars, you also have, as we now know, abundant water ice on Mars. You have an atmosphere of carbon dioxide. Again, you have the Martian soils, as well as hydrated minerals. So resources take on lots of different forms. So to get a little bit more specific, why do we care about space resources? Well, in just the inner solar system, and the inner solar system is defined as sort of the orbit of Jupiter and inward, the resources are nearly infinite compared to those available on Earth. And just to give you a couple of simple examples, the power that's output by the sun is 10 trillion times the power consumption of the entire human race right now. 10 trillion times. Just one large metallic asteroid, for example, 16 Psyche, which is actually going to be visited by a NASA mission in a few years, could supply the human needs for metals for millions of years at our current consumption rates. And I'm fond of saying that if we can bring the resources of just the inner solar system within the economic sphere of humankind, it'll be the next great economic revolution, as important and as profound as the agricultural revolution or the industrial revolution. It's truly remarkable. And just to point out on this picture here, that mission Lucy is going to visit these asteroids that are labeled Trojans and Greeks on this picture. So just kind of going from in to out in the solar system, you start with the sun. If you're in an astronomy class, you guys know this. Next out is Mercury, then Venus, then Earth, then Mars. Beyond Mars, there's this white cloud, which is the main asteroid belt. And then you have these weird locations here, about the same diameter as Jupiter's orbit, where you have Lagrange points, and I'll talk about Lagrange points coming up. But these areas where Jupiter's gravity and the sun's gravity combine to trap these asteroids in that kind of an orbit. So Lucy will be the first spacecraft to ever visit asteroids in the Trojan and Greek asteroid belts. So one of the most important resources in the inner solar system is water. And we now know that water is present on the poles of Mercury. So even that close to the sun, you can have water stable. Water is very abundant on Mars, we now know. It's contained in hydrated minerals and near-Earth asteroids. Perhaps most importantly, and I'll talk a lot more about this, water We now know water most likely exists near the poles of the moon. Water is a fabulous resource because it's essential for life. If humans are going to go out into the solar system and survive, we need water. We can break water apart to get oxygen, which we need for breathing air. And water also makes a really good radiation shielding. One of the difficulties in doing things in space is that we're not shielded from radiation from either the sun or the galaxy at large. If we split water into oxygen and hydrogen and then liquefy them, we have liquid oxygen, liquid hydrogen propellants, which are the most efficient chemical propellants known. We can also use water directly as propellant, either via steam. You can heat water up into steam and expel it out the back of a rocket nozzle, or you can heat it up even more and turn it into a plasma, which is basically a gas, and also expel it. And so I'm fond of saying that water is the oil of space. So the space economy, once we get it established, is going to run off of water. So it's super important to have water be so abundant in the inner solar system. A little bit about near-Earth asteroids. About 10 years or so ago, there were a number of companies that were established to go mine asteroids. They were thinking that if they found some metallic asteroids, that the platinum group metals, precious metals would be a really good business. None of those companies really made it, but asteroids will be part of that space economy. A lot of them are energetically easy to get to, which means you don't need a lot of propellant and big rockets to get to them. These are asteroids which are called near-Earth asteroids. They're in orbits that are very similar to Earth's orbit. They can be a little bit inside Earth's orbit, a little bit outside of Earth's orbit, or they can actually cross over Earth's orbit, which can make them dangerous. Many of them do contain water in the form of hydrated minerals. So this is water that's chemically bound to other minerals. If you heat it up enough, you can extract the water. This chart on the right shows a database that is maintained by the Jet Propulsion Lab, JPL, down in Pasadena, California, of all the asteroids that have been discovered. And you can see we're approaching 30,000 of these near-Earth asteroids. So there's a lot of objects out there. There's not that many that are big, say 1 kilometer across, but in total, there's quite a few. So I want to, from a resources standpoint, I want to focus the rest of this talk on the moon. The moon is our nearest neighbor. It's pretty easy to get to, easier to get to than these near-Earth asteroids, because the moon is, relative to Earth, is always in the same place. Asteroids are moving around. So if you're chasing asteroids, one analogy I like to use, it's a little bit like whaling. In the old days when, ships were out in the ocean chasing whales to get whale oil, which was, the whaling business in whale oil got put out of business by the discovery of fossil fuels. But, the ships have to chase the whales around the ocean. Similarly, if you're going for near-Earth asteroids, you got to go chase them around. And sometimes they're close to Earth, and so you have to time your trips to and from near-Earth asteroids based on their orbits. The moon is always in the same place. It's always 2 or 3 days away. And as it turns out, it's pretty rich in resources. So let's talk a little bit about the geography of the moon. Compared to Earth, it's pretty small. It's a little over 1% of the mass of the Earth. It's got about over 7% of the surface area of the Earth. Because it is light, its gravity is about 1/6 of Earth's gravity. So it's not zero. It's what's called tidally locked to Earth. And that means that when we look up in the sky and see the moon, we're always looking at the same side of the moon. So as the moon rotates around the Earth, the same side always faces toward us. That's what we call the near side of the moon. The other side that's on the back side that we can't see from Earth is called the far side of the moon. The moon does have a day. So the sun does go around the moon once every 28 days. At least it does relative to being on the moon. So you can't talk about the dark side of the moon. And I get a little irritated when you hear, news reporters talk about the Chinese landed on the dark side of the moon. No, they actually didn't. They landed on the far side of the moon because both sides of the moon receive sunlight about roughly the same amount of time. 14 days of sun followed by 14 days of night. So Dark Side of the Moon is a Pink Floyd song. It's not an actual thing. Because the moon has this cycle of 14 days of light to 14 days of dark, if you're in the sunlight, you experience really extreme temperature variations. And I'm going to speak in terms of Kelvin. So if you're at the equator of the moon, the temperature can vary during the night from 100 Kelvin, which is well below 0 Fahrenheit, all the way up to 390 Kelvin, which is above freezing. The moon also has no atmosphere at all to speak of. I mean, you can occasionally get, small, molecular level type stuff or atomic level stuff hovering above the surface of the moon, but that's about it. And one important point, and here's a new word for you probably, the obliquity of the moon is only 1.5 degrees. Obliquity is a fancy term for how much the moon is tilted relative to the direction of the sun. So we know that the Earth's tilted over 20 degrees, which is why we have seasons. The moon is not tilted relative to the sun very much. And what that means is if you're near the poles of the moon, and this picture on the right is showing a picture of the South Pole, depicting the average lighting. The sun is always on the horizon. So if you're at the poles of the moon, the sun, it's like being at one of the poles on Earth at one of the equinoxes. The sun will be right on the horizon all day long. So if you're at the poles of the moon, sun's always on the horizon, which means if you have a crater near one of the poles of the moon that's depressed from, into the surface, then there's never any sunlight. Those areas are called permanently shadowed regions. Another interesting feature of the poles of the moon, if you're on a mountaintop near the poles of the moon, like if you look right here in the crosshairs, there's kind of a circle to the lower right, that's Shackleton Crater. The rim of Shackleton Crater is brightly illuminated there. It's a mountaintop and it's nearly in continuous sunlight. So one of the reasons why NASA and other countries are interested in establishing bases at the poles of the moon is that you can have areas that have almost continuous sunlight, which is really important if you're using sunlight for electrical energy, if you're using solar power. The moon is rich in all kinds of resources. The graph on the right shows atomic compositions of samples from various Apollo landing sites. And a couple of those sites were in what are called the lower latitude mare regions. Mare is a Greek word that means ocean, which are kind of smooth plains of lava on the moon. Those areas are rich in titanium, which is that red sliver. All areas are rich in oxygen. Most of the minerals are oxides, but there's also all kinds of other stuff that'll be useful to human civilization as we get going. You've got aluminum, you've got iron, you got magnesium and silicon. Silicon obviously is a major constituent of solar panels or solar arrays. And in other places on the moon, you have rare earth elements, which are important for semiconductor manufacturing, things like potassium and phosphorus, which you would need for agriculture. There's been a lot of talk of helium-3, which is an isotope of helium that could be a constituent of clean burning fusion power. So if you fuse helium-3 together, fusion, like what occurs in the interior of the sun, helium-3 fusion generates no radioactive byproducts. So in the future, maybe 20, 30 years from now, when we get fusion to work as a technology, helium-3 fusion has the opportunity to provide abundant, completely clean power, which is why a lot of people have been interested in it. But helium-3 can be found in the surface of the moon. It's been implanted by the solar wind, so basically particles streaming out from the sun that get impinge on the lunar surface and get trapped. But again, most importantly for the near-term development of space is water that we see at the poles of the moon. So water exists, we believe, in these permanently shadowed regions near the poles of the moon. Because of that low obliquity, these permanently shadowed regions never see sunlight, and therefore they're extremely cold. You can get down to temperatures as low as 25 degrees Kelvin, 25 degrees above absolute zero, which is really, really cold. Some of the coldest places in the solar system. And the theory is that in over billions of years, you've had impacts, whether they're hydrated, asteroids with hydrated minerals, or potentially comets that have impacted the moon that contain water. That water gets vaporized. It forms a thin atmosphere around the moon for a short amount of time. Eventually it will get swept out into deep space by the solar wind, but enough of it could find its way into these cold areas near the poles. And once it gets into one of those areas, it gets trapped. It freezes into ice. And at those temperatures, 40 Kelvin to 100 Kelvin, that ice is stable for billions of years. And the presence of this ice has been confirmed by a number of remote sensing data sets. So we've had satellites that have orbited the moon with various sorts of instruments. This picture on the right shows some data from a neutron spectrometer that indicates the presence of hydrogen. And these areas in blue and purple are where you're getting hydrogen signatures. And it's believed that those represent either water or hydroxyl, which is OH. So it's either H2O or OH. So we have remote sensing data, but we directly confirmed the presence of ice back in 2009. And this was another one of my Atlas rockets. We launched the Lunar Reconnaissance Orbiter, LRO spacecraft that's actually still orbiting the moon today. And also present was a small Shepherd spacecraft that stayed attached to the upper stage of the rocket, the top stage of the rocket called Centaur. And this Shepherd stage guided Centaur over the course of about 3 months into an impact trajectory with the moon. And so this rocket stage went crashing into the Cabeus crater near the south pole of the moon. And Cabeus actually is this one that's that's indicated by 1S here, where that arrow is pointing. And right before impact, the Shepard spacecraft separated itself away, and it had instruments that it could interrogate the debris plume that was created by this impact. And through that experiment, we directly measured at that single location where the upper stage impacted that there was 5.6 plus or minus 1.9% by weight ice, water ice in that ejecta plume. So it's been confirmed directly that there is water in these cold regions near the lunar poles. Other recent data show that there, and this is data from an instrument called M3, which was on an Indian spacecraft called Chandrayaan, and then 2 instruments on the LRO spacecraft, that each one of those green dots represents ice exposures on the surface. So here we're saying not only is there ice, but there's ice actually on the surface. And these indications show that some of those surface deposits are up to 30% by weight. So we're pretty sure that the ice is there. But if we want to use it as either for sustaining life or converting it into rocket propellant, we got to figure out how to get it out. We got to go mine it. And, you know, in the old days on Earth, here in Colorado, you know, the gold miners basically had a mule and a pick, and that's all they needed, and a gold pan. You know, maybe we could put those guys in spacesuits and have them tromp around the moon, but that's probably not going to work. But luckily, the terrestrial resource industries have, over the years, developed proven processes for, you know, how do you go about extracting resources. And this chart shows some of the key terms in the resource extraction industry. Where we are today is on this upper middle called exploration results. And this chart has 2 axes. The vertical axis represents, as we go from the top to the bottom, increasing levels of geologic knowledge and confidence. What this means is, you know, do we know these deposits are there? You know, do we understand how deep they're buried, the different layers they're in, you know, how rich are these deposits? You know, that's all the stuff that geologists go do on Earth, you know. And if you're looking for petroleum, you would send drill rigs in and you drill and you understand the different layers of rocks and all of that kind of stuff. So that's the increasing levels of geologic knowledge. But then there's more to getting to getting a resource than just knowing about it. This horizontal axis includes all the other considerations that go into extracting a resource. You know, how do you know, what's the technology involved in mining it, processing that resource? What do we have to do? Are there economic considerations? Does anybody want the resource, and how much are they willing to pay for it? Are there legal issues? You know, on Earth, you got to get leases and mining claims and things like that. There's all the environmental issues. You know, what's the impact to the environment that's going to occur if we go extract this stuff? All of those other kind of things are called the modifying factors. And so if you have high geologic confidence and you also have knowledge of all those other things, you can get down to this lower right, which is called, you can declare this resource to be a proven reserve. And oftentimes you may have heard people, you know, talk about proven oil reserves or proven copper reserves. You know, those reserves, when you hear that term, don't think about it as this is all there is. Think about this is all we've been able to find and characterize and be able to label as economically extractable. So proven reserves are a moving target. It's always reflective of how much exploration has been done and the economic and other conditions that arise around it. Okay, so we're after this water in the poles and the moon. The first step is how do we go find it? How do we really get detailed knowledge about these deposits? You know, we've got some data from satellites. We have one hard data point when we crash something in there. But what we really need is, you know, on the ground surveys. And this can be done robotically, but the great challenge for doing things in these permanently shadowed regions is that there's no sunlight. And so how do we get energy? You know, one way that we've thought of, and these are some design concepts that we've come up with at the School of Mines, you could collect sunlight up on the crater rims where there's lots of sunlight. And then you can convert it into laser beams and beam it to a rover on the bottom in the dark who can receive it and then convert it back into electricity. So that's one idea. And I think it's a really good idea. Unfortunately, it doesn't scale up very well. So it's good for transmitting low amounts of energy, but there are other ideas. You know, maybe we can just put mirrors up on these crater rims and reflect the sunlight down into the interior. And this may seem like a crazy idea, but it's actually been put to use on Earth. You know, if you live in Norway in the far north, in a valley between mountain ridges, during the winter, you get no sunlight. And if you're a Norwegian villager, that makes you kind of sad. So the Norwegians, being clever people, went to the top of the ridge top and put some mirrors up there. And during the winter, those mirrors reflect sunlight down into the town. And now they have light. So the same idea could be applied to the moon. So one idea that I personally worked on is you have big mirrors upon the crater rims. They're called heliostats. They're slightly curved so that they actually concentrate the sunlight. That sunlight is beamed into the interior, where you would have a device like what I'm showing on the lower right, on this right-hand picture, where you have another mirror that then reflects that sunlight down through a transparent top of this dome onto the surface. And then that ice that's on the surface would be vaporized by the heat. It also penetrates a little ways into the subsurface. And then that vapor is confined in this cylindrical dome that we call a capture tent. And then it makes its way into these little tanks that you see on the outside, where it refreezes in the cold of that permanently shadowed region. So basically, all you need is sunlight to heat the surface. So that's one way you can extract ice. It's kind of a neat way because it doesn't involve, you know, heavy machinery or excavating. You're basically just using reflected sunlight to heat the surface that's otherwise been cold for billions of years. Here's an artist concept. I wrote a popular article about this a couple of years ago in the space magazine called Room, and they created this artwork. But you can see, you know, this is an industrial plant, maybe 20, 30 years in the future, where you have these enormous mirrors up on the crater rims, beaming sunlight down into the interior that's used to extract the ice. And then over here in the background, you can see a processing plant that's converting that water into propellant to be exported back into space. And then if those don't work, then there's always the nuclear option. And I say that a little bit tongue in cheek, but one of the facts of nuclear power generation, and now I'm talking about nuclear fission power, the sort of power that's in service all around the world today, is that for every watt of electrical energy you produce, nuclear fission plant produces about 4 watts of heat, waste heat. And that's why you have these big cooling ponds that are associated with nuclear power plants. And so it's how they're getting rid of all that extra heat. Well, heat's exactly what we need to get this ice out of the lunar soils. And so one idea is you have a nuclear fission plant that's providing the energy for propellant processing, and then you utilize that waste heat, which you would pipe in the form of a hot liquid, inside this same sort of dome-like structure, and then have radiators that you can see in that inset picture on the upper left that would radiate that heat onto the surface. And then, just as in the reflected sunlight approach, that vapor would be collected in these collection vessels attached to the outside of that dome. So there's a number of ways that we could go extract this ice. Of course, if none of these work, then the sort of brute force approach is that you bring in, the front end loaders and dig the soil up, put the soil into some sort of an oven, and you cook the water out that way. That's the brute force approach if these less intrusive approaches don't pan out. So this is more than just pretty pictures. We've actually done some testing at Colorado School of Mines in our laboratories that show we can extract this ice from surface heating. And the first step when you're doing these kind of experiments is you got to create simulants. The Apollo samples are pretty precious, but because we have analyzed the Apollo samples, we know the chemical constituents and sort of the grain size, makeup of lunar soils, and we can create facsimiles of those using lunar rocks. Basically, you take lava, basalt type rocks, and you crush it up, and you have a lunar simulant. But we took that kind of a simulant, mixed it with ice grains. This all has to happen in a freezer. So it's good to have students that you send into the freezer to mix this stuff up. Put it in a sample container like is shown on the lower left, and then put that sample container into a vacuum chamber to simulate the vacuum conditions on the moon, and then surround it with liquid nitrogen to get the temperatures down to cryogenic conditions, and then turn the lamps on and measure how much ice gets removed from these samples. So we've actually proven in our laboratories that this surface heating is effective at removing ice from lunar soils. All right, so once you get it out, then what are you going to do with it? It turns out that propellant, if we can find it and utilize it in space, is a game changer for space travel. And, I don't know if you guys have ever learned about the rocket equation, but basically, as you go farther and farther in space, the amount of propellant that you need to go increases exponentially with this parameter that's called delta V, which is just how much velocity you're adding to your rocket ship. And that fact, that exponential increase, is known as the tyranny of the rocket equation. That's why, rockets that go to the moon, like the old, the Apollo rockets, the Saturn V, the NASA's new SLS rocket, are so enormous because they have to take with them all the fuel they'll ever need to get there and to get back from Earth. And one way that I tell people to imagine the rocket equation is, imagine if you're going to drive from Medford, Oregon to Washington, D.C., and there are no gas stations on the way. So all the gas you need to get to Washington and to get back, you have to take with you when you leave. So, your ordinary little car is not going to work. You'd run out of gas, by the time you got to the Idaho border. So you need to bring more gas, but if you bring more gas, your gas mileage goes down. So you need a bigger vehicle, which gets even lower gas mileage. And so you can see it kind of snowballs in the bad direction. That's the essence of the rocket equation right there. But if you have gas stations along the way, then you can do everything with small vehicles. You don't need a big giant Saturn V. And this curve on the right just gives you some of the math that's behind that. If you refuel one time, 2 times, or 3 times, you basically take that exponential increase and flatten it out. And what that means is that every space mission beyond low Earth orbit would benefit substantially from having space propellant available in space. And so we can get cost reductions going to the moon. Just going from the Earth to the moon, refueling one time gives you a factor of 3 cost reduction. So it's a big deal. It's a big deal, and that's why developing these water resources is so important. So to kind of understand a little bit about how all this works, I'm going to digress a bit and give you a little bit of a lesson on the geography of cis-lunar space. So cis-lunar space means the space in and around the Earth and the Moon system. And so this is a picture of that geography. The white lines represent contour lines of gravitational potential energy. So you can think of that as sort of height. And the fact of gravitation, of planets is that they sit at the bottom of a gravity well. They're at the bottom of a pit. And to get into space, you have to climb out of that pit. And therefore, you need big rockets with big rocket engines. In a system like the Earth and the Moon, you have 2 gravity wells, one for the Earth and the other one for the Moon. The Moon being so much of a smaller body, its gravity well, its pit is a lot less. Within a two-body system, there are these interesting points that are called Lagrange points, after the French mathematician that first characterized them. And the obvious one is what's called Lagrange Point One. And it sits between the Earth and the Moon. And it represents the spot where the gravitational pull of the Earth is exactly balanced by the gravitational pull of the Moon. So it's kind of like a flat spot. You can park there, and if you're used to hiking in the mountains with topographic maps, L1 is a saddle point. So it's the same kind of place you would get if you go through a mountain pass, right? It goes up in 2 directions and down in 2 directions. In this case, for L1, it goes down toward the Earth and down toward the Moon, and then it goes up in these other directions. So you can actually put something there and have it be stable. The other thing I'll point out is that this picture is actually in a frame of reference that's rotating with the Moon. So the Moon rotates about the Earth, and so this picture would rotate with the Moon. And so in that rotating frame, you have this fictional force, and I don't know if you guys have taken physics or not, but you have a fictitious force in a rotating frame called the centrifugal force that's actually pushing outward. It's the same force when you spin an object on the end of a string. So there's another point similar to L1 on the other side of the Moon called L2, where this centrifugal outward force is balanced by the inward gravitational force of the Earth and the Moon. Another one, similar point on the other side of the Earth called L3. And then these points L4 and L5 are where the outward force, centrifugal force, is balanced by the combination of the gravitational pull of the Earth and the gravitational pull of the Moon. And these points are actually stable. So what that means is if you park something in L4 or L5, it'll stay there. And remember all the way back, to the beginning of this talk, those Greeks and Hilda asteroids, those things are at those stable Lagrange points of the Jupiter-Sun system. And so those asteroids have been trapped in those points, and they've been there probably for billions of years. All right, so once you understand that geography, then getting around cislunar space becomes a matter of how much delta V do you need, which through the rocket equation is equivalent to how much propellant do you need. And you can see if you start on the left-hand side, just getting from Earth to low Earth orbit, and you don't need to worry about these units, but they're in kilometers per second. Delta V is 9.5. And to get out to geosynchronous orbit from low Earth orbit is another 4.3. So, it's almost 15 to get from low Earth orbit to geosynchronous orbit where a communication satellite would be. But then if you go and look on the other side, getting from the surface of the moon to say EML1 right there is about 2.5. And then to get from EML1 to geosynchronous orbit is another 1.4. You can add those together. So it's about 3.9. So it's actually a lot easier to get from the surface of the moon to Earth orbit than it is to get from Earth to Earth orbit. So that kind of brings things into focus a little bit. So then you can imagine the economics of mining water, turning it into propellant, and exporting that propellant around cislunar space. So this chart kind of shows you some of the things you might be doing. You're mining this water, processing it as propellant on the surface of the moon. You're exporting propellant to EML1. EML1, you can have dispatched tankers that would refuel other rocket stages that are moving from Earth to the moon or Earth to somewhere else. You can also be water mining these near-Earth asteroids and bringing their water back. So you can imagine a whole system of creating propellant and distributing around cislunar space to be used to refuel all sorts of other spacecraft. And in that sense, it's very analogous to the way we mine and refine, petroleum products here on Earth and distribute those, all around the world for use in homes, home heating, or automobiles. I'm getting close to the end here. So one of the things that we've done recently is create an architecture for what this logistics node might look like at EML1 that has propellant storage and processing, and you would park it in an orbit around EML1. You would do water to propellant refining. You would also store both water and liquid oxygen, liquid hydrogen propellants, transfer those propellants to tankers for upper stage refueling. And then an exciting thing is use water to refuel satellites in geosynchronous orbit. Today, when a geosynchronous satellite runs out of propellant, it's dead and it no longer has value, and they move it off to a parking orbit and it becomes space junk. In the future, you can refuel those satellites and use them over and over again. And that's actually, a new area of endeavor that a lot of companies are working on. And then the idea for refueling outbound stages is you'd have a tanker that leaves from this EML1 propellant depot. You launch a payload in an upper stage into a rendezvous orbit. The tanker would rendezvous with that upper stage and payload, and then that payload would go off to some future destination. And that economics is extremely favorable. You get enormous cost reductions by doing rocket missions this way. And then finally, once you start building up this kind of infrastructure, if you can utilize lunar resources, you can start imagining building large space structures out of lunar materials. And one example of this is space solar power. So, there's a big push for greener energy on Earth. Solar power is great, the downside to solar power is that it only works during the day. And it doesn't work very much when it's cloudy. It's probably cloudy a lot in Oregon. And like in Texas last year, if your solar panels get snowed on, they're useless. But if you can put those solar panels in orbit, like this picture here is a concept called Space Solar Power Satellite Alpha that produces over 2 gigawatts of electrical power into the grid. It's an enormous object. It would be over 10,000 metric tons if we launched it from Earth, and therefore not feasible. But if you can mine all those materials on the moon and assemble them in space, then the cost of this thing becomes very affordable. And you can actually meet or beat energy prices into the grid. And the beauty of this is that it's unlimited energy, solar energy, available 24/7. It's not bothered by weather. It's always in the sunlight. And it's inexhaustible and completely green. So you can imagine a future where all of our energy use or energy demands are provided by solar energy beamed from space, from big solar power satellites constructed from lunar materials. And that's a future of unlimited energy, almost essentially inexhaustible and completely green. All right, so that kind of gets me to the conclusions. If we can figure out how to bring these resources of space in to the economic sphere of humankind, then that leads to a future of unprecedented prosperity and flourishing. You can imagine a future post-scarcity future where resources are not scarce and everybody is rich. And with that, I'll read this one last quote from this guy, John Marburger, who was President's science advisor of President Bush back in 2006. The moon has unique significance for all space applications for a reason that, to my amazement, is hardly ever discussed in popular accounts of space policy. The moon is the closest source of material that lies far up Earth's gravity well. Anything that can be made from lunar materials at a cost comparable to Earth manufacture has an enormous overall cost advantage compared with objects lifted from Earth's surface. The greatest value of the moon lies neither in science nor in exploration, but in its material. And with that, I'll be happy to take questions.
All right, let's give Dr. Sowers a hand.
All right, so did I leave enough time for questions?
I think we do, yeah. Yeah, we got plenty of time. I've got a chair up here. I'm gonna have kids come up to the chair. I wanted to ask one thing. You guys be shy. Let's get some questions up here. I wanted to ask you something. I flew on the Sophia back in 2014, the Stratospheric Observatory. I kind of keep up with their science, and they seem to have found quite a bit of soil outside of the polar regions, water in the soil. They seem
there's water, that's been implanted by the solar wind again, in the lunar soils, even at lower latitudes. But those are in very low abundance.
Okay.
So you're talking about parts per million.
I see.
Versus 4%, which is
Right. Yeah, it wasn't like ice. I remember the what I read, and maybe it hadn't been verified, was about 8 to 12 ounces per cubic meter of soil is what they thought they found in their.
Yeah, that seems a little high, but
Yeah,
again, it's not just is it there, but can you extract it and process it economically?
Exactly. All right, who's got a question? Come on up, Robbie. Robbie's coming up.
Okay, so for the satellite that we were just talking, or the solar power that we were just talking about, wouldn't it be also easier to get the materials from Earth and ship it into space and assemble it there, would that work?
It's more expensive.
Okay.
So Earth's gravity well, go back to, and I know I presented you a lot of material rapidly. It's a little like drinking out of a fire hose, but the cost to move material from Earth into that, and again, that kind of a satellite would want to be in geosynchronous orbit. But it's much more expensive to bring materials from Earth into geosynchronous orbit than it would be to bring them from the moon.
Okay. All right.
And so it's a matter of economics. You could do it. And in fact, there's active research and technology development by both the military side and mostly on the military side into these kind of satellites. And you first would probably demonstrate that technology by launching it from Earth. So you would launch some demonstration satellites, but when it came time to really building a big, sort of industrial scale, gigawatt scale power plant that would, put energy into the Earth's grid, you would probably want to bring those materials from the moon.
All right. Okay. Thank you.
Come on up, Meshach. While Meshach's coming up, I was going to ask you, I was fascinated by that last slide where you collected the solar power in space and then beam it down in microwaves. I remember hearing from Dr. Richard Smalley, you probably remember him. He was the first person I heard talk about the Rectina.
Mm-hmm.
What kind of death ray would that be? Would that be something that would cause environmental issues?
No, you don't want to aim a death ray at the Earth from space. I mean, maybe somebody does, the evil James Bond villain does, but we don't want to do that. So
where would you collect that?
It's a microwave. It's diffuse microwaves.
Mm-hmm.
So they're not harmful to birds flying through it. And it's not harmful to vegetation or anything. And this Rectina is basically a grid of wires that you could mount up on poles, above a cornfield or a wheat field or somewhere like that. So you're not, unlike solar panels on Earth, you don't have to consume land to put them out there. And the grid of wires is not very dense. I mean, the grids are like a meter across. And the wavelengths of these microwaves is pretty long.
Gotcha.
So a bunch of studies have been done on that, and you can tune it so that it would be absolutely safe.
Fantastic. That's Meshach. All right, here's the camera.
Okay, so you described in the rocket equation that refueling in space is more efficient. So why isn't there any fuel stations like in L1 or in orbit?
Because we haven't gotten there yet.
Okay.
So, there are companies that are working on that kind of technology, and it's really beneficial. Once it's a little bit of a chicken and the egg thing, right? So right now, no rockets are designed to be refueled because there's no fuel in space. And one reason there's no fuel in space is because there's no rockets to be refueled. So it's one of those things where it has to get started. And then actually it is starting to happen with satellites in geosynchronous orbit. There was a Northrop Grumman just a year or two ago actually flew a satellite into geosynchronous orbit that latched on to a Intelsat communication satellite that was out of fuel. And it didn't transfer the fuel, but it had its own fuel. So it became a new source to reactivate that spacecraft. So it basically latched onto it and became its propulsion system. But that's kind of the first baby step in getting there. And, people are actively working on creating those capabilities.
Okay. And then also
NASA's just last year, 2 years ago, invested about $300 million in technologies to store and transfer fuels in orbit. So yeah, we're getting there. We're just not there yet.
And then in the beginning, you talked about the asteroid cluster and then Trojan and Greek clusters. Why are we going after Greek and Trojan clusters instead of the asteroid belt?
Because we've never been there before and it's a science mission. We've actually had satellites explore the main asteroid belt. And there was a mission called Dawn that visited Vesta and Ceres asteroids in the main asteroid belt. And so this one is to go a little bit further and to just see what's there. And then later this decade, there'll be another mission that goes to visit that metallic asteroid called 16 Psyche, which will be pretty exciting.
Yeah. Okay, one last one. For water transport, why doesn't NASA split it into hydrogen and oxygen so it can be compressed?
So water is a lot more dense than liquid oxygen, liquid hydrogen. So, you know, it's a matter of logistics and again, economics, which you would transport and store. You know, I kind of think that you would, if you're producing it on the surface of the moon in one of these permanently shadowed regions, you would turn it into liquid oxygen, liquid hydrogen, because you can store it there pretty easily because it's really cold. And then the other thing, and this is kind of a subtlety of the way rockets work, is that water comes in the hydrogen oxygen ratio of 8:1, right? You got 2 hydrogens, 1 oxygen, and you just do the math ratio and it's 8 times as mass of oxygen as you have hydrogen. Rocket engines prefer to burn those propellants in a ratio of like 5.5:1. So water actually has a lot more oxygen than you really need for propellant.
Yeah.
Another question up here. While another kid's coming up, I was wondering, you know, I didn't really hear about refueling in space till I heard, you know, SpaceX's plan on going to Mars and colonizing. I was wondering, you probably were on the ground floor. How long has that been a concept of refueling to get rid of the tyranny of the rocket equation?
People have known about it since as long as they started thinking about the rocket equation, right?
Right.
It's sort of an obvious one.
Sure, right.
But you know, then the question comes, where does that fuel come from and how do you actually refuel it?
Right.
And so you kind of need some infrastructure in place to really make it all work.
Exactly. Here comes Emily.
Hi, so my question is the ELM1, is that going to be a module that will dock with the gateway?
So the gateway is not going to EML1.
Oh, okay.
It's in what's called and this is getting sort of technical, it's near rectilinear halo orbit.
Huh.
So you can say that fast, you know, 5 times.
Good luck. Right.
But it's an orbit that goes, you know, if you're looking down on the Earth and the Moon, and it would be an orbit that's going around the Moon in and out of the plane of the page.
Huh.
And so you can always see it from Earth. That was one of their requirements. So I always wanted to be able to see it from Earth. And then it was also chosen for reasons that are not all that obvious, but have to do with how long it takes to get from the Moon to that location and whether or not it would be accessible by the SLS and Orion spacecraft that NASA was already making.
Right.
If it was me, if I had been making that decision, I would have parked it at EML1.
Okay. So EML1 is an orbit then, basically?
It's a location.
A location.
And to actually be there, because it's not a stable point, it's a saddle point, like I was saying. You would actually be in what's called a halo orbit about EML1. So you'd be going around EML1. The actual location is a point. It's a mathematical point. But if you put something there, it'd be orbiting around and around it.
Interesting. So is Gateway going to go out at L2 then?
No, like I said, if you were looking at that picture that I showed, then it would be the same distance away as the moon, but an orbit around the moon
Oh, okay.
that's going perpendicular to the line between the Earth and the moon.
Oh, okay. Thank you.
Gotcha. Fascinating. Do you have faith in the Gateway and the Artemis program? I mean, I know you're on the ground floor of all that. Does it seem like a working plan?
I'm really happy that NASA's now focused on the moon.
Yeah.
You know, I'm all for exploring Mars. You know, 10 years ago, you know, it was all about going to Mars. And when under President Obama, he actually said that, you know, we're not going to go back to the surface of the moon because we've already been.
It makes sense.
But I'm glad that we've now switched and the moon is the focus of the program. And, you know, everybody can argue about details of this piece of hardware or that piece of hardware. But, you know, the fact that we're focused on going back to the moon is the right focus. And that aligns us with the whole rest of the world. Everybody's going to the moon. China's going to the moon. Russia's going to the moon. Europe's going to the moon. Japan's going to the moon. We're all going to the moon, which means I think we can make it happen.
Yeah.
And then once you have lunar resources available, then getting to Mars becomes a lot easier. If you have a gas station on the way to Mars, things get a lot easier going to Mars.
Yeah, isn't it good to be an old timer too? Remember when we were kids and they said the moon was bone dry? Remember all that? Yeah. That's the bell. Hey, everybody, let's give him one last round of applause. Thank you, Dr. Sowers.
Thank you, guys.
Sure enjoyed that. Thank you.
Great.
Yeah, that was fantastic. Thanks a lot.
Yeah, so my plan would be to do the same exact thing for your next week.
That'd be yeah, that'll be great. That'll be a different audience. They'll be more of our age, most of them. We'll get a few kids in there too, but I'll show this to the rest of my classes. So thank you so much. You know, the public school teacher is a horse race. We're, 5 minutes, it's another class. So.
Yep, I understand. I'll let you go.
No. Thank you. Thank you so much. That was really interesting. Thank you.
All right, great. Thanks.
Bye. Take care. See you next week.